Continuing our discussion on isomers, let's turn our attention to enantiomers. And let's review our flow chart. First, we determined that it is an isomer by finding that it has the same chemical formula. Then, if we have the same bond connections, they are known as stereoisomers. But if the bonds are not the same by rotating around a single bond, then they are some type of configurational isomer. And then further, if there are mirror images of each other, then we have enantiomers. So let's look at some enantiomers and how to identify them. And when we do, we will draw, probably an easiest way to do this is to draw both of them. So an enantiomer is a non-superimposable mirror image of its partner. So let's draw a couple of molecules and we'll draw the mirror image for that. So I'm going to pick a carbon that has a bunch of halogens around it because they're simple. And then we have the hydrogen behind. And then I'll just draw the mirror image next to it. So I start and I draw the same type of bond, but I just flip it over. So the fluorine was coming out of the page. It's still coming out of the page. The chlorine and the bromine were in the page, but now I've turned them around. And then the hydrogen was going behind. These are mirror images of each other, and we're not able to superimpose them on top of each other. Now, this is a little bit difficult to see just by looking at paper. So I've made some models of these. So if we choose this red one to be the bromine and this orange one to be the chlorine and this green one to be the fluorine, and then behind we have the hydrogen, I have constructed two mirror images. Let's see here. Yep. So chlorine's there, fluorine, bromine, and behind's the hydrogen. Now, the question is, can we superimpose these two molecules? So I'll just kind of try to bring them together, and then I'll look, and when I rotate it around, I've got the carbon in the same position, and I have the bromines in the same position, and the chlorines are. But there's a mismatch between where the fluorines and hydrogens are. So we cannot directly align these completely. They're non-superimposable. And if I were to try to match up, let's see here, the hydrogen and the fluorine, well, now the bromine and the chlorine are mismatched. So these are an example of an enantiomer. And one of the ways that you can easily tell that you'll have an enantiomer is if you have one carbon atom in a molecule that has 4 different groups around it, it will have an enantiomer pair. So just the nature of how this works. Now, in some later videos, I will go over the naming of these compounds, but I will do a very short explanation of those right now. We determine the priority of these molecules, and we kind of think of them as rotating around the lowest priority group. And they go by the mass of the group, or the atomic number, and then secondary, the mass of it. So if you have isomers, it goes isotopes. If you have isotopes, the higher mass isotope is the one that's given priority. This is the first priority group. This is the second, third, and then the fourth. And as long as the fourth is sitting behind, then we can just count and we can see that this molecule goes in kind of a right turn or a clockwise direction. And the molecule over here goes in the counterclockwise direction, or a left-hand turn. And we've given these names, and unfortunately D and L were already taken because that's what rotates light either left or right, and so we couldn't use those. So instead they used R and S. The R stands for rectus, or right turn, right-handed, and the S stands for sinister, or improper, or left-handed. That's a traditional kind of situation that I didn't come up with, but that's the origin of the R and the S name. Let's draw some more molecules and we'll check to see if they are enantiomers. So we'll draw some mirror images and then we'll make a model of them and then check, see if we can superimpose them. Oh. So now I have two of the groups that are different. Two of them are the same, two hydrogens on here. So let's look at our model kit with these molecules. Okay, in this case, let's choose the orange to be the bromine and the green to be the chlorine. And then I have my hydrogens. And let's see here, there's our mirror image right here. So there's the mirror image, but let's see, can we align these and superimpose them? So if I line them up like this, we can indeed superimpose these. Since we can, these are not enantiomers. In fact, these are the same molecule. That this is not an isomer of each other. It's the same. So it really does help to have the model kit. A couple more examples. So let's look at some substituted cyclopropanes. So we'll draw one where they're on opposite sides of the molecule. And then we'll draw it again where the chlorines are on the same side. And then I'll grab the model kit real quick. So first, I have this pair where the chlorines are on opposite sides of the molecule. And so these are, in fact, mirror images of each other. And then let's see if we can superimpose them on top of each other. So when I look at that, I try to line up as much as I can, and I'm having difficulty, right? Because it's not possible. They're on opposite sides. And if I were to try to rotate this around, I still have the same problem. They're still on opposite sides of the molecule. So these are enantiomers of each other because they are non-superimposable mirror images. Now I have to switch my model kit a little bit to make the other version. So there's one of them made. And now I have the other one. So here are those mirror images, but I can very easily superimpose them so that everything lines up in the same positions. So these are not enantiomers. So over on this side of the page, these are examples of enantiomers. These are not. One of the ways that you can tell that something will not be an enantiomer is if there is a mirror plane contained inside of the molecule. Then you will not have an enantiomer. And we can see that mirror plane right here, right? If I had a mirror, I could reflect this side over there and that side back there. Since it has an internal mirror plane, you'll be able to superimpose it on itself or on a mirror image like so. This molecule up here also has a mirror plane. And if I align this like so, and we're looking down the mirror plane right here. So if I reflected this, these hydrogens would reflect into each other. And all of these atoms right here would be contained in the mirror plane. They wouldn't move. So another example of having an internal mirror plane of symmetry, therefore not being an enantiomer. So that is one way to determine if it's possible, or help you determine if they are enantiomers. If you can find a mirror plane within the molecule, then it won't be. Please be careful though with how you draw the molecules. Sometimes if you're trying to do it just on paper without the aid of a model kit, it can be difficult to determine if they are enantiomers. Sometimes even with a good amount of experience. So with that, this is a video about enantiomers and how to determine whether they're enantiomers or not, just by drawing their mirror images, looking at model kits to see what we're doing. Thank you, and we'll see you in the next video.